Neural networks are the computational architecture that underpins all of modern artificial intelligence. Loosely inspired by the structure of biological neurons in the brain, artificial neural networks are systems of interconnected mathematical units that learn to transform inputs into outputs by adjusting the strengths of their connections through a process called training. From recognizing faces in photographs to generating human-like text, from predicting financial markets to folding proteins, every major AI capability of our era emerges from neural networks trained on data. Understanding how they work is essential for anyone who wants to understand why AI is so powerful and where its limits lie. Let us examine the fundamental components and mechanisms of neural networks and understand why this architecture is so uniquely suited to learning from complex, high-dimensional data. 5 core concepts define how neural networks are structured, how they learn, and how they transform raw inputs into meaningful predictions and outputs. A neural network is organized into layers: an input layer that receives raw data, one or more hidden layers that progressively transform the representation, and an output layer that produces the final prediction or generation. Each layer contains a number of neurons, mathematical units that receive a weighted sum of their inputs and apply a transformation. Deep neural networks have many hidden layers, each learning increasingly abstract features of the input. The first layers of a vision network might detect edges. The middle layers might detect shapes. The final layers might detect specific objects. This hierarchical feature learning is what makes deep networks so expressive. The weights of a neural network are the learnable parameters that determine how strongly each neuron's output influences the neurons in the next layer. A bias term is an additional learnable parameter that shifts the activation of a neuron independently of its inputs, giving the network greater flexibility. Before training, weights are typically initialized randomly. During training, they are adjusted iteratively to minimize the difference between the network's predictions and the correct answers. A large neural network may contain billions of weights, each one a single number, and it is the collective, coordinated values of all these weights that constitute the knowledge the network has learned. Without nonlinearity, a neural network with multiple layers would be mathematically equivalent to a single linear transformation, no more expressive than linear regression. Activation functions introduce nonlinearity by applying a nonlinear transformation to each neuron's weighted input sum. The rectified linear unit, or ReLU, is the most widely used activation function in modern networks. It outputs 0 for negative inputs and the input value itself for positive inputs. This simple function, applied across millions of neurons, enables neural networks to approximate arbitrarily complex functions and learn the nonlinear patterns that characterize real-world data. The forward pass is the process of computing a neural network's prediction for a given input. Data flows from the input layer through each successive hidden layer, with each neuron computing its weighted sum of inputs and applying its activation function, until the output layer produces the final result. During training, the forward pass is performed for each batch of training examples to compute predictions. These predictions are then compared to the true labels using a loss function, such as cross-entropy for classification or mean-squared error for regression, that quantifies how far the network's predictions are from the correct answers. Backpropagation is the algorithm that makes neural network training possible. After the forward pass computes the loss, backpropagation uses the chain rule of calculus to compute the gradient of the loss with respect to every weight in the network, determining how much each weight contributed to the prediction error. These gradients are then used by an optimization algorithm, most commonly stochastic gradient descent or ADAM, to update the weights in the direction that reduces the loss. This cycle of forward pass, loss computation, backpropagation, and weight update is repeated millions of times on batches of training data until the network's predictions are accurate. For fundamental terms that define the mechanics of how neural networks learn and represent knowledge, the artificial neuron is modeled, at a high level of abstraction, on the biological neuron. It receives numerical signals from multiple input connections, each weighted by a learned parameter. It sums these weighted signals, adds a bias term, and applies an activation function to produce its output. This output is then transmitted to every neuron in the next layer. Despite this simple computation, networks of millions or billions of neurons, organized into many layers and trained on large data sets, produce systems capable of extraordinarily sophisticated behavior. The neuron is a humble unit, but its collective power, when multiplied across billions of connections and trained with backpropagation, is the foundation of modern AI. Weights are the memory of a neural network. Before training begins, weights are initialized to small random values. Through the training process, they are iteratively updated in response to the errors the network makes on training examples. Over millions of update steps, the weights converge to values that allow the network to make accurate predictions on new, unseen data. The entire knowledge that a language model has about grammar, facts, reasoning patterns, and the world is encoded in the numerical values of its billions of weights. When we say a model is trained, what we mean precisely is that its weights have been optimized to minimize prediction error on the training data. The choice of activation function has profound implications for the behavior and trainability of a neural network. Early networks used sigmoid and tan functions, which map any input to a bounded range. However, these functions cause the vanishing gradient problem in deep networks. Gradients become extremely small as they are backpropagated through many layers, making training of deep networks very slow or impossible. ReLU solved this problem by providing a gradient of 1 for all positive inputs, allowing gradients to flow freely through deep networks. Variants like leaky ReLU, YeLU, and GeLU offer further improvements and are used in modern LLMs and vision transformers. Backpropagation is one of the most important algorithmic discoveries in the history of computing. Developed in the 1970s and popularized in the 1980s, it provides an efficient method for computing the gradient of a scalar loss function with respect to every parameter in a network of arbitrary depth. The algorithm works by propagating error signals backward through the network layer by layer, using the chain rule to decompose the gradient into a product of local gradients at each layer. Modern deep learning frameworks like PyTorch and TensorFlow implement automatic differentiation, which performs backpropagation automatically for any computational graph, freeing researchers to focus on network architecture rather than manual gradient derivation. Let us now examine how different neural network architectures are applied to real-world problems across computer vision, language, games, and creative generation. Neural network architectures have been tailored to different data types and tasks, producing specialized systems that achieve superhuman performance across a remarkable range of domains. Convolutional neural networks, or CNNs, are specialized architectures designed to process grid-structured data, such as images. Rather than connecting every neuron to every input pixel, which would require an infeasible number of parameters, convolutional layers apply small learned filters that scan across the image spatially, detecting local patterns such as edges, textures, and shapes. This parameter sharing makes CNNs dramatically more efficient than fully connected networks for image tasks and introduces a useful inductive bias. The same pattern should be recognized regardless of where it appears in the image. CNNs underpin facial recognition, medical imaging, autonomous vehicle perception, and industrial quality control systems. The transformer architecture, with its self-attention mechanism, has become the dominant neural network architecture for processing sequential data. In language tasks, transformer-based models like BERT and GPT learn to represent the meaning of words in context, capture grammatical structure, and generate coherent multi-paragraph text. The same architecture, adapted as the vision transformer, achieves state-of-the-art results on image classification. The transformer's scalability and generality have made it the unified architecture that researchers now apply to language, vision, audio, video, code, and scientific data simultaneously. Reinforcement learning trains neural networks through a fundamentally different paradigm. The network learns by interacting with an environment and receiving reward signals for successful actions. DeepMind's AlphaGo and AlphaZero demonstrated that reinforcement learning combined with deep neural networks could master the game of Go at a level far beyond the best human players. More recently, reinforcement learning has been applied to robotics, training neural networks to control robotic arms for manipulation tasks, and to training LLMs through reinforcement learning from human feedback, where human preferences guide the model toward more helpful and accurate behavior. Generative neural networks learn to create new data, images, audio, video, text, that resembles their training distribution. Generative adversarial networks, or GANs, use two competing networks, a generator that creates synthetic data and a discriminator that tries to distinguish synthetic from real data. The adversarial training dynamic drives the generator to produce increasingly realistic outputs. Diffusion models, which underpin modern image generators like DALL-E, Midjourney, and Stable Diffusion, learn to reverse a gradual noise-adding process, generating images by progressively denoising random noise guided by text prompts. Both architectures have transformed creative industries and raised important questions about authorship and intellectual property. Let us bring together the essential points from our exploration of neural networks. To explore more key concepts in generative AI, check the link in the description. If you found this helpful, please like and subscribe. Thank you for watching. If you found this helpful, please like and subscribe. See you in the next video.